Okay, so now that we kind of understand what an action potential is, you can kind of visualize it a little bit like this. You've got a situation where you've got sodium channels going into the neuron and potassium leaving in like a wave-like fashion, and it goes all the way down the axon. Okay. So if we look at these voltage-gated sodium channels, they live all the way along unmyelinated axons. Okay, and that causes the signal to travel in a kind of a slow way, because as it says here, when one little bit of the axon becomes depolarized, so it hits -55, that opens up the voltage-gated sodium channels just next to it. Okay. Now, that means that the next bit of the axon will now become -55, which opens up the next voltage-gated sodium channels, which makes that bit -55, which opens up the next adjacent sodium voltage-gated sodium channels. It's like having to light a fuse every little step of the way. Now, in an axon that does have myelin, you have the advantage where the voltage-gated sodium channels are concentrated in these little areas between the myelin. So this means that lots and lots of sodium then depolarizes or makes -55 this whole bit. And so that means that this section then now becomes -55 millivolts and then opens up the voltage-gated sodium channels there. Okay? It's a more efficient way, because the depolarization here, this -55, starts here but affects all the way to this kind of region. So we're opening up our voltage-gated sodium channels here, so much so, with so much sodium, that you end up depolarizing or bringing this little spot to -55. Okay, so what we want to do now is we actually want to think about what happens when the action potential travels down the axon. What happens when we reach the end? Okay, so how do we get this axon or this neuron to communicate with this one? So this is what happens here. So what happens here is called synaptic transmission. So I'm going to use an animation for this because it's a really good animation and it's got sound. Okay, are we ready? And I will stop and start it to explain it to you.
Neurons transmit chemical signals across synapses, like the one shown in this electron micrograph. We can identify the dendrite of the receiving or postsynaptic cell, as well as two presynaptic nerve terminals loaded with synaptic vesicles.
That's fine, don't worry too much about that.
Separating the pre- and postsynaptic cells. The synapse converts the electrical signal of the action potential in the presynaptic cell into a chemical signal.
Okay, so what we need to do, so this is the presynaptic neuron, okay, presynaptic nerve terminal. So this is where the action potential comes down, and then this is the next neuron along in the chain. Okay, so you've got the axon action potential coming down, neuron number 1, and it's going to communicate with neuron number 2. So let's see what happens.
When an action potential reaches a nerve terminal, it opens voltage-gated calcium channels in the plasma membrane.
Okay, so step 1. The action potential comes down to the ends of the neuron. Sorry, I just got a phone call. It comes down to the end of the neuron. The first thing that happens is that there's another protein here. Now this protein is called the voltage-gated calcium channel. Okay? Now this guy opens up its door when a specific voltage is reached. Okay? So the action potential comes down and then it opens up this channel here. Now this protein will only allow calcium through. Let's have a look and see.
Allowing calcium ions to flow into the terminal. The increased calcium in the nerve terminal stimulates synaptic vesicles to fuse with the plasma membrane.
All right, so now we've got calcium coming into our axon terminals. As you can see, this is a calcium ion, okay? Now what that calcium ion does, it pushes these little vesicles out, okay? Now these little bubbles here, they contain neurotransmitter, all right? And we have many of the neurotransmitter vesicles there. So they contain a neurotransmitter. So the action potential comes down, calcium comes in, and then these little vesicles are pushed out,
releasing their neurotransmitter cargo into the synaptic cleft.
So neurons never are in contact with each other. They are close to each other, but they never touch. So that means that the neurotransmitter diffuses into the synaptic cleft.
The released neurotransmitters diffuse across the synaptic cleft, where they bind to and open the transmitter-gated ion channels in the plasma membrane of the postsynaptic cell.
Okay, so once the neurotransmitter diffuses down to the next neuron, to the dendrite of the next neuron, it causes a protein channel to open, okay? And that allows ions into the next neuron. And that is essentially how it works. So let's have a look here. Number 1, the action potential comes down. The calcium channels open, calcium comes in, pushes these little vesicles out, and the vesicles containing neurotransmitter fuse with the membrane and neurotransmitter is released, and then there's a protein involved, okay? There's a protein involved. When the neurotransmitter binds to this protein, it opens up a channel, okay? So this is neuron number 1, this is neuron number 2, the next neuron along in the chain. So here is another picture here, see? Neuron number 1, neuron number 2. Here are our little synaptic vesicles. They are the little packets that contain neurotransmitter. Okay, so there's 2 kinds of synapses. One that makes your neuron more likely to fire an action potential, and another one that makes your neuron less likely to fire an action potential. Acetylcholine is, we will leave that one later for another example. Let's have a look at these ones. I know these pictures are a bit blurry, sorry. So if you have a synapse that is excitatory, okay, what happens is that in the next neuron, sodium enters, okay, and that's going to make my second neuron in the chain more positive. So for an example, glutamate is an excitatory neurotransmitter, okay. So this, if an excitatory neurotransmitter causes sodium to enter the next neuron, then it's going to be an excitatory effect, which means that this neuron is going to become more positive and maybe kick off an action potential. If you have an inhibitory synapse or an inhibitory neurotransmitter, the opposite happens. So, for example, GABA is an inhibitory neurotransmitter. That means that when the neurotransmitter binds to receptors in the postsynaptic cell, it opens up protein channels that allows negative ions through. So when negative ions go into our neuron, it's going to make our neuron more negative, which is going to be less likely to fire an action potential. All right, so once the neurotransmitter has actually been released, we actually really need to get rid of it. We should only just leave it there for the exact amount of time. So what do we do with it? The neurotransmitter can just kind of diffuse away and the neuroglia can take care of it. Or we've got enzymes that can come and break down the neurotransmitter, okay? And the other thing that we can do, we have little proteins that grab the little neurotransmitter from in there and then pop it back in here, and we can reuse it in a different vesicle. Voila!